The first section, which is the historical uses of metals, would be focusing on how man equipped metals and used metals for everyday work throughout the centuries. So let's get started. Now, it started with the Stone Age. During the Stone Age, man used stone for most of their weapons and tools. Then comes the Copper Age. This is from 5000 BCE to 3000 BCE. And during this time, copper was the main material used for tools and weapons. Then comes the Bronze Age. Bronze is an alloy of copper, and it was from 3000 BCE to 1000 BCE. During this time, bronze was the main metal used. And after the Bronze Age comes the Iron Age. This is from 1000 BCE. During the Iron Age, alloys of iron as well as iron in its pure form are used for structures, tools, and weapons. The first metals to be used. The first metals to be used were gold, silver, and copper. Gold and silver are known as native metals, and that is because they were first used. But they were used for ornaments, jewellery, as well as tools. Now, why were gold, silver, and copper used first? Well, because they exist in their elemental state. What that means is they don't chemically combine with other metals, and they just exist as pure gold, pure silver, and pure copper. But this is not the case with other metals. Most metals do chemically combine, and they form what you call minerals. Minerals are mixtures of metals that have chemically combined with one another. They require a large amount of energy input for separation. And this is because they are chemically bonded. That means they have ionic or covalent bonds combining them together. Now, when we look at minerals in a much detailed way, a large input of energy is required to break and rearrange the bonds. They're strong chemical bonds, so they require a large amount of energy. It was in around 5000 BCE in the Middle East that copper was extracted from malachite. It's a green copper containing mineral. The picture is a diagram of malachite, which is first heated to extract copper. And this was the beginning of the Copper Age. In the beginning of the 19th century, a scientist named Humphrey Davy extracted active metals such as potassium, magnesium, and calcium using electrolytic procedures. Now, this uses electricity. So you use electrical energy to extract metals from their ores. With potassium, magnesium, and calcium, they are quite active metals. That means they don't usually exist in their elemental state because they're very likely to combine with another element to form a compound. Extraction of metals using other metals. So there are three ways you can extract metals. One, heat, which we discussed with copper, and also with electrolytic procedures, which is mainly used with active metals, and also when you can use other metals to extract your metal. And this is called chemical energy, the use of chemical energy to extract metals. For example, we can extract titanium from its salt titanium chloride by reacting it with magnesium or sodium. If we were to write a chemical equation for this, we would have titanium chloride, which would react with the sodium metal to form sodium chloride and the titanium metal. So, when you're writing a chemical equation, it is always good to balance the equation. So, we'll start off with titanium. Titanium, there is one molecule of titanium here, and there's one molecule of titanium here. So the titanium is balanced. Now we would move to chlorine. There are 4 chlorine molecules and only one chlorine molecule here, which means that we need to add a 4 in front of the NaCl. Now balancing the Na, there's only one sodium molecule here and there's 4 sodium molecules here, which means that you need to add a 4 in front of the Na on this side. So now this side balances that side of the equation. So this is the chemical equation for what is summarized up here in words. and that uses chemical energy to extract metals. However, pure titanium was not isolated until 1910, or the impure forms did exist a century ago. Now we're focusing on alloys. Alloys are what you call mixtures of metals. They contain two or more metals combined together. Properties of metals could be significantly altered by combining them with other elements. That is to say, for example, copper is a soft metal, but when you combine it with tin, it becomes harder, and this is called an alloy. The alloy is called bronze for copper. So we'll look at some examples of alloys. We have bronze, which has tin and copper. There's brass, and also steel, which is an alloy of iron. During the Copper Age, which was from 5000 BCE to 3000 BCE, that happened 8,000 years ago in the Middle East, they used two forms of copper. One was native copper, and the other is blue-green copper. Native copper was much harder than gold, and therefore it was used for tools, and also it was used for jewellery. Now, blue-green copper was used for decorative purposes, and both of these copper was extracted from its ore using the process called smelting. Smelting is a process that was used to convert copper minerals into metallic copper. Now we would look at smelting in a greater depth here. First, there is the process of crushing the metal. By crushing the metal, you would increase the surface area. So what you do is, by increasing the surface area, you make more area for the heat to dissipate. This means that it effectively heats up. Then you use high temperatures to strongly heat the crushed metal. This happens in a reducing environment, rich in carbon and low in oxygen. So you would have these conditions for the smelting of copper. The third step is to mix the copper with the glassy slag formed from the quartz in the ore body. Then, for further improvements, copper is now being extracted in its liquid form, so it's easier for us to cast them into tools. Some uses of copper include tools. So copper was used for axe heads, spears, and arrowheads during the Copper Age. It was also used for kitchen utensils such as plates and cups. For cooking pots, because it was a great thermal conductor. Due to its high thermal conductivity, it cooked food better. And mirrors, because of its luster and its ability to reflect light. Copper ores. Now we would chemically see the chemistry behind the extraction of copper from its ores. Now first you would heat the copper ore, which is hydroxy copper carbonate. When you heat it up, it decomposes to copper oxide, carbon dioxide, and water. So if you write this in a chemical equation, it would look like this. You would have your hydroxy copper carbonate, which is this part, decomposing in the presence of heat to form copper oxide, carbon dioxide, and water. Note that there are symbols next to each of them. Those are the states. It is very important to write states when you're writing a chemical equation. So the S denotes solid, the G denotes gas, and L denotes liquid. So the hydroxy copper carbonate is going to be in its solid form. The copper oxide is again going to be in the solid form. Carbon dioxide, gaseous, and water is going to be in liquid form. Now what happens after this is we react the copper oxide with carbon, and this forms copper and carbon dioxide, and that's how you would extract copper from hydroxy copper carbonate. For this reaction, you would have a chemical equation looking like this. So the copper oxide from here would come down there. It'll react with carbon to produce copper and carbon dioxide. Note that you write your states and always balance the equation. Also, you can extract copper from chalcopyrite. Now, when you're extracting copper from chalcopyrite, copper comes out in its molten state. That means it's liquid. Now this is the chemical equation for chalcopyrite. You would heat it up in the presence of oxygen and in the presence of sand. So silicon dioxide is sand. And this would produce copper in its liquid form, sulfur dioxide gas, and also ferrosolite, which is in its liquid form. Again, always write the states and balance your equations. Now, alloys of copper. There are two alloys of copper. One is tin bronze and one is arsenic bronze. Both are forms of bronze. Tin bronze has copper and tin, while arsenic bronze is composed of copper and arsenic. And they're widely used as well. Now comes the Iron Age. The properties were known by ancient people from meteoric iron. Before the Iron Age, iron was not well known. However, meteoric iron, which is iron from meteorites, did exist. But meteoric iron was corrosion resistant, while normal iron is not. Extracting metallic iron from iron ore was developed 3,500 years ago. This required high temperatures that mixed the iron ore with charcoal to produce iron. The use of high temperatures was to break the chemical bonds, and it is very important to highlight this, to break the chemical bonds, because in an iron ore, the iron is intact with the rest of the metals due to chemical bonds. Smelting of iron. Now, smelting of iron involves two steps. The first step does not require iron, but it gives off carbon monoxide. So we start off with carbon. We heat the carbon, or we burn the carbon in the presence of oxygen. This would give us carbon monoxide. Now again, when you're writing a chemical equation, always write your states. So the carbon is in solid form, the oxygen is in gaseous form, and the carbon monoxide is in gaseous form. Now we're going to balance the equation. We'll first balance the carbon. There's one carbon molecule here and one carbon molecule here, so the carbons are balanced. But there's two oxygen molecules here, while there's only one oxygen here. That means we have to add one more oxygen, and you do that by adding a 2 in front of the CO. But now there's two carbons on this side and only one carbon on this side. So to balance it even further, you would add a 2 in front of the C. This is a balanced chemical equation. Now what you do is you have the carbon monoxide from this reaction. You use that carbon monoxide, extract iron from the iron ore. So you have iron ore with carbon monoxide giving iron and carbon dioxide. Now again, ore is in its solid form, the carbon monoxide is gaseous, iron is in solid form when you extract it, and the carbon dioxide gas is formed as well. Again, always balance your equation. Now with the process mentioned earlier, there was a problem because carbon was present in the iron. Now this meant impure iron. So to overcome this problem, what they did was they hammered the iron when it was red hot to squeeze out the impurities. But further development happened when a blast furnace was developed. A blast furnace used high temperatures. It would melt the iron, which was later molded. So here is an animation of the blast furnace. You have the raw material coming in, and it would get melted in these high temperatures here. Molten iron would exit out from here, the molten slag from this end, and we have the waste gases excreted from each of these chambers. There's always blasts of hot air being pressurized in, and this is to keep the temperatures at 1,000 degrees Celsius. However, 2,000 years later, the technology did improve and iron strips were created. This was used to mold swords and to strengthen chariot wheels. Now, this is the end of the first section. We talked about the Stone Age, the Bronze Age, the Copper Age, and the Iron Age. And also we talked about how you extract metal from heating, electrolytic processes, as well as chemical processes.